Hello, my name is Joe Cloud. On behalf of my co-authors, I am presenting our work, Lunar Excavator Emission Operations using Dynamic Movement Primitives. The authors are affiliated with NASA's John F. Kennedy Space Center and the University of Texas at Arlington. Establishing an affordable human presence on the moon will require making use of the resources available on the surface. This is called in-situ resource utilization, or ISRU. Many ISRU technologies rely on the use of robots to carry out tasks like excavation and construction on the surface. However, there are hazards to operating on the moon, such as rocks, and the robots cannot rely on persistent real-time human interaction, so they will need some degree of autonomy to carry out their tasks. In future ISRU missions, robots may be tasked with driving in various test patterns, including the circular ones we address in our work. Consequently, there is a need to encode these test trajectories in a way that is robust to the hazards of the lunar surface. In this work, we use dynamic movement primitives to represent these trajectories. The dynamic movement primitive, or DMP, is a mathematical framework designed to encapsulate complex sequences of motion and generalized building block trajectories. This allows us to specify new start and goal locations as well as velocity scaling values while retaining the primitive behavior. Here we show the one-dimensional spring damper system for DMPs and the forcing term FVS, which we learn using locally weighted regression. We can also add other terms to DMPs, such as for obstacle avoidance. One of the contributions of our work is the adaptation of the steering angle-based obstacle avoidance approach introduced in reference 23 to do obstacle avoidance with circular trajectories. In practice, the original formulation uses a threshold on obstacles further away from the goal than the robot. This assumption does not hold in circular pattern driving. In our approach, shown in the third equation, we weigh the distance of the obstacles and add a threshold to localize the obstacles that are considered. Since we also focus on circular primitives, we bias the term to the interior of the circle so that the trajectories are nominally shorter than the base DMP or other approaches. Here we see the results of our method. Execution A shows the original obstacle avoidance formulation in blue with the same parameters as we used in our method. We separately optimized and used the new gains throughout the rest of the experiment, which we show in execution B and C, and more results are in the paper. Note that because the original formulation considers all obstacles together, it can be inadvertently steered into collisions, such as the cases in execution C. Finally, we show the results in our 3D lunar simulation called SEELO. Here, we randomly initialize the surface with a high density of large rocks. 3 robots are superimposed in the video to show synchronized execution of their respective primitives. You can see the robots that aren't using our obstacle avoidance method, such as the original OA method or no OA method, collide with rocks at certain points, and some points cause the robot to stop operation. Despite the dense population of rocks, our modified method is able to successfully traverse the environment without hitting any obstacles. Here we show the video sped up by 4 times real time. Thank you.